Welcome back to Math 104. Suppose you do find out that a certain survey participant is living on campus. As a result, in light of this information, are you more inclined or less inclined to think that he or she is a history major than if you hadn't found out that he or she lives on campus? As in the previous problems, we need to compare a conditional probability to an unconditional probability. The chance of being a history major in light of the new information versus the chance of being a history major without any new information. We just computed the conditional probability of approximately 0.0833, and the probability of H itself is exactly 0.1, because there are 100 history majors out of 1,000 survey participants total, and therefore the conditional probability is less than the unconditional probability. In light of the new information, I am less inclined to think that this person is a history major than if I hadn't known anything about their on-campus, off-campus status. Here's another example which is helpful for understanding conditional probability. We will consider the following 5 events: E, that the blue die shows a 2, F, that the red die shows a 2, G, that the sum equals 10, H, that the sum equals 7, and I, that the red die shows a 5. So the following is a systematic listing, as usual, of the 36 different possible outcomes in the sample space. The 36 equally likely possible outcomes of this experiment. Our convention will be that within each pair, the first number represents the number on the red die, and the second is the number on the blue die. So 1 on the red, 4 on the blue is different from 4 on the red, 1 on the blue. First, let's quickly find the probabilities of each of these events in their own right, and then we'll look at conditional probabilities. So first, the probability of E, that the blue die shows a 6. This last column contains all the outcomes in the event E. There are 6 equally likely ways for the blue die to show a 6, hence a 6 out of 36, or 1/6 probability of E. For F, the event that the red die shows a 2, there are also 6 equally likely outcomes, so it too has a probability of 6 over 36, or 1/6. The event G involves a sum. We have to look for all the outcomes in which the sum equals 10, and there turn out to be 3 of them. That's 3 out of 36. H, the event that the sum equals 7, that has 6 different outcomes. They lie along this diagonal over here. That gives us a 6 out of 36, or again, a 1 out of 6 probability that H occurs. And finally, I, the event that the red die shows a 5. I realize this diagram is getting a little bit crowded, but I hope the different colors help. The event that the red die shows a 5, that also has a 6 over 36, which is 1/6 probability. Now, picture the moment of rolling the dice, and imagine that as you're rolling, the red die pops out of your hand, and when it lands, it shows a 2. That means you haven't finished rolling the dice, because the blue die is still in your hand, but you have partial information about the outcome of the experiment. So let's look at the events E, that the blue die shows a 6, and F, that the red die shows a 2. F has happened. Whatever happens with the blue die, it is true that the event F occurs on this roll of the dice. That means that when we compute probability of E given F, or the probability of something else given F, that conditioning on F reflects the fact that we know F has already happened. This is a really concrete way of thinking about conditional probability. You're in the middle of the experiment and you find out partial information. This is like the previous example where we talked about catching a glimpse of somebody's transcript and seeing that they're a junior, or seeing that they're not a junior, but not knowing whether they live on campus, or whether they're a history major. Here too, the fact that the red die is already known to show a 2 is partial information. Now let's do the comparison. How does our new assessment of the probability of E, in light of the fact that F is known to occur, how does that compare to what the probability of E is, in and of itself, without any information about F occurring? We've already found that the probability of E equals 1/6. So now let's find the probability of E given F. That equals the probability of E intersect F divided by the probability of F. We always divide by the probability of the second event, the one that we are conditioning on, the event that we are zooming in on. E intersect F, the event that the blue die shows a 6 and the red die shows a 2, that consists of this outcome and this outcome only. That's 1 out of 36 divided by 6 out of 36, which is 1/6. Another way to look at this is that the event F consists just of these 6 outcomes. When we zoom in just on those 6 outcomes and ask how many outcomes are in E intersect F as a fraction of all of F, well, it's 1 out of these 6. So this 1/6 makes sense. What does this tell us? It tells us that these probabilities are equal. So the probability of E given F is equal to the probability of E. That's interesting. We haven't seen an example like that yet. What does that mean for our follow-up question? Our follow-up question is, what is the effect of knowing that F has occurred on your new assessment of the likelihood of E? As it turns out, there is no effect. Knowing that the red die has popped out of my hand and shown a 2 has no impact on my assessment of how likely it is that the blue die will show a 6. That makes sense. What happens with the red die should not have any impact on what happens with the blue die. This partial information about the outcome of the experiment actually tells me nothing about E by itself. This is an important idea, and it deserves a new piece of terminology. We say that the event E is independent of the event F if the conditional probability of E given F, equals the unconditional probability of E. In other words, to say that E is independent of F means that if we know that F has occurred, this knowledge does not change our assessment of how likely it is that E has occurred. Our new assessment of the likelihood of E, in light of the fact that F has occurred, that's the conditional probability, is the same as the old assessment. The old assessment is regardless of F, knowing nothing about F. In this example, it makes perfectly good sense that what happens on the red die and what happens on the blue die are independent of one another. We have used the word independent before in this course, but we've used it in an informal way. Now we're giving it a definition. Let's do another comparison. F is still the event that the red die shows a 2. That's the event that we're conditioning on because that's the partial information we have about how the experiment will turn out. And G is the event that the sum equals 10. Compute G given F. Is this greater than, less than, or equal to P of G? Let's recall where F lives. F is the event consisting of these 6 outcomes. And then G is the event consisting of these 3 outcomes. What does that tell us? It tells us that when we go to compute the probability of G given F and apply the formula probability of G intersect F divided by probability of F, this numerator, the probability of G intersect F, that's 0. Because there is no intersection, there are no outcomes in common between F and G. So this is 0 out of 1/6, which is just 0. Whereas P of G is not 0. P of G we found earlier was 3 out of 36, or 1/12. So the conditional probability is less than the unconditional probability. Once again, if you think about it, this makes sense. Before the red die ever popped out of my hand and displayed a 2, I had a certain idea of how likely it is that the sum will equal 10. That idea was 1/12. But now that the red die has popped out of my hand and displayed a 2, that changes my assessment of my chances of rolling a 10. It's now become impossible. Once one of the dice shows a 2, there's no way the sum could be as large as 10. So the occurrence of F, the appearance of a 2, causes the event G to become impossible. So my new assessment is indeed less. I become much more pessimistic about the chance of G happening in light of F occurring than I was before I knew anything about F. What is the effect of knowing that F has occurred on your new assessment of the likelihood of G? It makes G impossible. That is a very large impact. We can now ask, is G independent of F? No, certainly not. Because the probability of G given F is not equal to the probability of G. That's our definition. If these probabilities were equal, then we would say that G is independent of F, but they are not equal. So no, G is not independent of F. Before going on to the next video, answer the following question. Now we're going to compare F and H, where H is the event that the sum equals 7. So compute the probability of H given F, figure out is it greater than, less than, or equal to the probability of H, and then the follow-up question, what is the effect of knowing that F has occurred on your new assessment of the likelihood of H? Is H independent of F?